The current Copenhagen interpretation of the double-slit experiment. The Copenhagen interpretation is one of the oldest and most widely discussed interpretations of quantum mechanics, developed primarily by Niels Bohr and Werner Heisenberg in the 1920s. It provides a framework for understanding phenomena like the double-slit experiment, emphasizing concepts like wavefunction collapse and the role of observation. Here's how the Copenhagen interpretation applies to the double-slit experiment. 1. Wave-particle duality. In the double-slit experiment, particles, e.g., electrons or photons, exhibit wave-like behavior when not observed, creating an interference pattern on a detection screen. According to the Copenhagen interpretation, the particle's wavefunction represents a probability amplitude, describing all possible paths the particle can take. When unobserved, the particle exists in a superposition of states, passing through both slits simultaneously. 2. Role of observation. If a measurement device is placed at the slits to determine through which slit the particle passes, the interference pattern disappears, and a pattern corresponding to particle-like behavior, two distinct clusters, emerges. The act of measurement collapses the wavefunction, forcing the particle into a definite state, e.g., passed through slit A or passed through slit B. This collapse eliminates the superposition responsible for the interference pattern. 3. Complementarity. The Copenhagen interpretation highlights the principle of complementarity, which states that particles exhibit either wave-like or particle-like behavior depending on the experimental setup but never both simultaneously. The choice of measurement determines which aspect, wave or particle, becomes evident. 4. Probabilistic nature. The interference pattern seen on the detection screen is interpreted as a manifestation of the wavefunction's probabilities. The intensity of the pattern at any point corresponds to the likelihood of the particle being detected there. Key takeaways. Reality is contextual. The nature of quantum objects depends on how we choose to observe them. Wavefunction collapse. Observation plays an active role in defining the state of a quantum system, transitioning it from a superposition to a definite state. Uncertainty and indeterminacy. The exact outcome of where a particle lands is probabilistic, not deterministic. Modern discussion. While the Copenhagen interpretation remains influential, it has been challenged by alternative interpretations, such as the many-worlds interpretation, pilot wave theory, and objective collapse models. These interpretations seek to address questions like the nature of wavefunction collapse and the role of consciousness or measurement in quantum mechanics.